In this video, we discuss the derivatives of our 6 trig functions. And we've already derived the derivative of sine of x. And we said that it was cosine of x. We derived this algebraically using the limit definition in video 2.2 on this playlist. This video, we will find the derivatives of cosine and tangent algebraically, and then we'll save the derivatives of secant, cosecant, and cotangent for after we learn the quotient rule and the chain rule. One of the things that we use to derive that the sine of x, derivative of the sine of x is equal to cosine of x, was Euler's formula. So Euler's formula says, I said Euler's formula. Yeah, that's right. Euler's formula is that e to the I times some angle is cosine of that angle plus I times sine of that angle. Now, if I replace the angle with a plus b, that turns out to be cosine of a plus b plus I times sine of a plus b. Now, we remember that if we want to multiply two exponents that have the same base, all we have to do is add the exponents. So an alternate form of writing e to the I times a plus b is this e to the IA times e to the IB. E to the IA can be written this way, just applying Euler's formula once. And then e to the IB can be written this way, also applying Euler's formula. So I've got this times this. And then if we distribute, first times first is a real term. So I'll write that here, cosine of A times cosine of B. And last times last is also a real term because I times I is I squared. So we'll have I sine of A times I sine of B. So that's negative sine of A sine of B. So the real part of this expression is cosine of A cosine of B minus sine of A sine of B. And the imaginary part comes from the outer times outer and inner times inner terms. So outer times outer is cosine of A sine of B times I, and then inner times inner is sine of A cosine of B times I. If I factor out the I get this. So I want you to see that the real part of e to the I times A plus B is cosine of AB, and it can also be written in this form. So that gives us an identity for the value of cosine of a sum. It's cosine of the first angle times cosine of the second angle minus sine of the angle times sine of the first angle times sine of the second. And similarly, the imaginary part of e to the I times the quantity a plus b is just given by this. So sine of a plus b can actually be written in terms of cosine of a and cosine of a and cosine of b and sine of a and sine of b using this identity here. We've got a sine and a cosine, and one of them is evaluated at one angle, the other one is evaluated at the other angle, and then you just flip the angles or switch the angles and then you add. So I end up with cosine of A times sine of B plus cosine of B times sine of A. Now we can use each of these in our derivations of the derivative for cosine and sine. We use this in the derivation for the derivative of sine of x in video 2.2, and we'll need this for our derivation of the derivative of cosine of b algebraically, or excuse me, cosine of x algebraically. So let's derive this algebraically, and then we'll also look at some graphs and see how the geometry is consistent with these algebraic derivations. So the derivative of cosine of x is defined to be the limit as x approaches 0 of my function evaluated at x plus delta x minus my function evaluated at x, all divided by delta x. Now, since this is the cosine of a sum, we'll apply this formula. So you have cosine of the first angle times cosine of the second minus sine of the first angle times sine of the second. I'm really not sure how insightful this is, but it is how we would derive it algebraically. All right. Now, if I look at this term and this term, they have a cosine of x in common, so I can factor that out. So this is the limit as delta x approaches 0 of cosine of x times the quantity cosine of delta x minus 1. Because cosine of x times cosine of delta x gives me this term, and cosine of x times -1 gives me that. Then we have minus sine of x times sine of delta x. And all of that is divided by delta x. So if we wanted to, we could divide this first quantity by delta x and then second quantity by delta x and subtract. It's just like saying, 2 plus 5 divided by 3 is the same as 2 over 5 plus 3 over 5. Like, you can split the numerator and keep the common denominator. It's totally legal algebraically. Now, we have a couple of important limits. We know that the limit as theta approaches 0 of 1 minus cosine of theta divided by theta equals 0. And we know that the limit as theta approaches 0 of sine of theta over theta equals 1. And we also know that the limit of the sum is the sum of the limits, and the limit of a product is the product of the limits. And here, what we're interested in is this expression as delta x approaches 0. So we're thinking of x as fixed at this point, and delta x is getting smaller and smaller. It's approaching 0, either from the left or from the right. So with that in mind, I can split this up. I can write this as a product and sum of terms. And with looking at this first expression, first I see that there's a cosine of x here, so that can be factored out of the limit entirely. And then I'll have the limit as delta x approaches 0 of this divided by this. And that's a function of delta x. And then we're subtracting the limit of this, because the limit of the difference is the difference of the limit. But again, x is constant at this point. We're thinking of it as fixed. So we can factor that sine of x out and then bring the limit notation in. This is actually sine of x times the limit as delta x approaches 0 of sine of delta x divided by delta x. And then because of these two known limits, we know that this limit is 1 and this limit is 0. Now I know that this is in a slightly different order, but if I multiply by -1, the opposite of 0 is 0. So this is going to go to 0 as well. So we end up with cosine times 0 minus sine of x times 1. And so we find that the derivative of cosine of x is negative sine of x. And that's it. So we've derived that using the limit definition. I don't know how insightful that is, but it does allow us, the limit definition does allow us to find those two derivatives. Now, I think it's a little bit more insightful to just explore these definitions geometrically. This is a graph of y equals sine of x. At least for a couple of periods. I've got one period here, a second period there, and then a half of a period there. Maybe a little bit more than half of a period there. This is pi, this is 2 pi. This is negative pi, that's negative 2 pi. And if I want to graph the derivative, I can think about the tangent line right here and say, okay, what does the slope of the tangent line seem to be? Well, I know it's a positive number because that graph or that line is sloping up as we go from left to right. It turns out that the slope happens to be 1. The slope is 1 there as well. And the slope is 1 there as well. Similarly, at negative pi and pi, my tangent lines are sloping down. As you look at the graph, those tangent lines decrease as you go from left to right. So at negative pi, we get a negative value for our derivative, and it turns out that negative value is -1. At pi, got a value of -1 as well. And then at 3 pi, we get a value of -1. And then we can also look at the tangent lines at the top and at the bottom. Well, we know that those tangent lines are horizontal, so they all have a slope of 0. So at -3 pi/2, we get 0. At -pi/2, we get 0. At pi/2, we get 0. At -3 pi/2, we get 0. At 5 pi/2, we get 0, and so on. Now, if I connect those with a smooth curve, hopefully you recognize it. It looks like the sine graph just shifted, right? It starts at 1, then it's 0, then it goes to -1, then it's 0, and it goes back to 1 at 2 pi. It turns out that that's cosine of x. So it's the derivative of sine of x is cosine of x. And the sort of geometric interpretation by just looking at the function itself, drawing those tangent lines, then thinking about the slope of each tangent line allowed us to infer that this was the general shape. A little bit harder to infer the actual slope without a grid. But if we had a grid, we would be able to sort of calculate that slope by just looking at rise over run. And turns out as x increases by 1, y increases by 1. So the slope is 1 here, and the slope is -1 here. So the derivative of sine is cosine. Similarly, we can look at the derivative of cosine geometrically. All right. So if we draw tangent lines at the top and bottom of each of these hills and valleys for a cosine graph, this is y prime or y equals cosine. We know that the derivative graph should have a function value of 0 here and here and here and here and here. So at x equals -2 pi, the derivative should be 0. And at x equals pi, the derivative should be 0. And at x equals 0, the derivative should be 0. At x equals pi, the derivative should be 0. And then at x equals 2 pi, the derivative should be 0. Then you might say, okay, what are the other interesting points? Well, here and here, at all of those odd multiples of pi, we see we've got a negative slope here and here. It turns out that slope is -1. So if I graph that, graphing that point there and that point there, and then if I look at this point where the cosine graph crosses the x-axis, those slopes are positive ones. So I'm actually literally plotting the point x equals -pi/2, y prime equals 1. So I'm just finding out what the derivative is, I'm estimating it, and then I'm plotting that y value. So if this slope is 1, I want to plot y equals 1. If this slope is 1, I want to plot y equals 1. Then we connect those points with a smooth curve. You ask yourself, well, what does that graph look like? It looks a lot like the sine graph, right? Except instead of going up first and then down, it goes down first and then up. Turns out that that's equal to negative sine of x, which is consistent with our derivation algebraically. So the derivative of sine is cosine, and the derivative of cosine is negative sine. Now the derivative of tangent is a little bit harder to see. The tangent is going to be undefined at all the odd multiples of pi/2. The tangent graph looks roughly like this. And it repeats itself. And it's a little bit hard to see, and I don't know if I've drawn it very well, but this branch, it just repeats itself. It repeats every repeats every pi unit starting at negative pi over 2. So it's undefined whenever cosine is 0. And then we get something that looks like this. All of these slopes are positive, and it turns out that they're equal to 1. So if I plot y equals 1 here, the graph of the derivative passes through those points. Now, if you look at the slope of this graph, the slope just gets larger and larger. If I keep drawing tangent lines, this tangent lines get steeper. So I might have a line with a slope of, 1.5, or a slope with, or a tangent line with a slope of 2, and then up here I might have a tangent line with a slope of 10. But the slopes get larger, and so the graph looks like that for the derivative. And then similarly, these slopes are all positive. I might have a tangent line with a slope of 1/2, and then, or a tangent line with a slope of 1, and then like 1.5, and then 2, and then 10, and 100. The slopes are just getting larger and larger, but they're all positive because if I draw a tangent line here, those lines are all increasing as you move from left to right. And so the graph looks like that. And it repeats because all those branches are the same. That's y equals tangent of x. We might say to ourselves, y prime equals what? That kind of looks like secant of x, but it's always positive. Got the secant looks like this, and then it has a branch that goes down, and then a branch that goes up, and then a branch that goes down, and it flips. With the derivative of tangent, they're all positive, and the function values are all between 1 and infinity. So we might be wondering, like, what is that? It looks like it might be a secant or related to secant, but it's positive all the time. It's not negative. To figure that out, we could try using the limit definition. I actually haven't done this one yet, so I'm going to try it, and we'll see. We'll see how it goes. If we make a mistake or are unable to do it, we'll learn from our mistake. So we've got the derivative with respect to x of tangent of x is the limit as delta x goes to 0 of tangent of x plus delta x minus tangent of x all divided by delta x. Now, I don't have any identity for tangent of x plus delta x, but I do know the tangent of sine, or I do know the sine of a sum and the cosine of a sum. So I could use the sine of a sum and the cosine of a sum to rewrite that, but there's going to be a lot of terms. We're going to end up with a lot there. So this would be sine of x plus delta x divided by cosine of x plus delta x minus sine of x divided by cosine of x all divided by delta x. You say, okay, well, it's still a 0 over 0 indeterminate. If I substitute in delta x equals 0, I get tangent of x minus tangent of x, so I get 0. And then I have a 0 in the denominator. Now we call this a complex fraction because we've got fractions within a fraction. We want to get rid of the fractions within a fraction. We multiply by the denominators of the smaller fractions. So we're going to multiply the numerator and denominator by cosine of x plus delta x times cosine of x. And that's legal as long as we do the same thing in the, we do that in the numerator, clear the fractions, but we have to do the same thing in the denominator so that our fraction has the same values. It's called multiplying by a well-chosen one. And then this has multiple terms since we're subtracting. So this term needs to be multiplied by that, and then this term needs to be multiplied by that. And the denominator is just a product, so there's not really anything to simplify yet. Now I multiply this times this. These cosines will reduce, and I just end up with this sine of x plus delta x multiplied by cosine of x. And then when I multiply this by this, the cosines will reduce, and I end up with a sine of x times the cosine of x plus delta x. All right, so that's what we have. Now we're still not ready to simplify yet. If we substitute in delta x equals 0, I've got sine of x times cosine of x minus sine of x times cosine of x. And then I've got that's a 0 in the numerator. And then as delta x goes to 0, we have a 0 times cosine squared x in the denominator. So we're not quite there yet. But this can be rewritten. Well, actually, is there a way to simplify further? If I take this and divide by this, the cosines reduce and I just end up with that over that, which is not helpful. If I take this and divide by this, the cosine or the cosines of x plus delta x reduce and I just end up with that divided by that, which is what I have. So that doesn't help. Let's try just writing out sine of x plus delta x. See if that gets us anywhere. Sine of x plus delta x is equal to this. But we're going to use x equals a and b equals delta x. So we've got cosine of x times sine of delta x plus cosine of delta x divided by sine of x, or times sine of x, excuse me. All of that is multiplied by cosine of x. And then we're subtracting sine of x times cosine of a sum. And the cosine of a sum can be found this way. Cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle. And cosine of x times cosine of delta x minus sine of x times sine of delta x. All divided by this. Now I notice that if I distribute this cosine here and here, and I distribute this sine here and here, I've got some like terms. First times first is going to give me a cosine squared x. Times sine of delta x. And then it's actually not a binomial, so it's just this first term times the cosine gives us this. And then this times this. Well, I've got a cosine of delta x, sine of x and cosine of x. There's nothing that matches there, so we just leave that alone. But I notice this is a negative sine of x cosine of x times cosine of delta x. And since multiplication is commutative, this expression is the same as that expression. It's just subtracting something from itself, so those guys are gone. And then I've got negative sine of x times this term. Negative times a negative is going to be a positive, and then I'm going to have a sine squared x times sine of delta x. I'm excited. I've got a cosine squared times sine of delta x and a sine squared times sine of delta x. That makes me excited because I see sort of how it's going to simplify in a minute. And then I've got delta x times cosine of x plus delta x, all divided or all multiplied by cosine of x. And then this numerator has a sine of delta x in common. And then I've got a cosine squared x plus sine squared x there, all divided by this. And cosine squared x plus sine squared x is 1. So we end up with this limit. Now as delta x approaches 0, we get sine of 0, which is 0, divided by 0. So this is still a 0 over 0 in determinate form. But we'd like to get rid of that. So I think I want to expand this cosine of x plus delta x, cosine of a sum, using that identity again. We'll see if that helps. I'm not 100% sure. I'm going to factor that cosine of x out front. So we've got delta x times cosine of x. And this is cosine of the first angle times cosine of the second angle minus sine of the first angle times sine of the second angle. First times first is going to give us that cosine squared times the cosine of delta x. And then this guy times this is going to give me a minus x sine of delta x times sine of x cosine of x. Now if I substitute in delta x equals 0, I have a 0 here and a 0 here and a 0 here. So I still have a 0 over 0 in determinant form. Now, this was a delta x that was factored out before. I distributed it, but that didn't really help us. One thing I can do to rewrite this is to regroup. I've got sine of delta x divided by delta x, and we know from earlier lessons from the last chapter that the limit as delta x approaches 0 of sine of delta x over delta x is equal to 1. If I plug in delta x equals 0, I have a 0 over 0 indeterminate form, but we were able to prove using the squeeze theorem that that's equal to 1. So this divided by that is 1, so I can move that delta x up to the numerator. This is sine of delta x divided by delta x. All divided by cosine squared x times cosine of delta x minus sine of delta x times sine of x times cosine of x. And this approaches 1. This approaches 1. This approaches 0. So what we end up with is 1 divided by cosine squared x times 1 minus 0. So we end up with 1 over cosine squared x. And 1 over cosine of x is secant of x. So it ends up being secant squared x, which is consistent with our picture. We said that looks a lot like secant, but it's not secant because it's always positive. Well, it turns out that it's equal to secant squared x. So we've got the derivative of tangent of x is equal to secant squared x. And these other derivatives will be derived using the quotient rule later. And we can rederive the tangent of x derivative using the quotient rule as well after we learn the quotient rule. Now it turns out that the derivative of secant of x is secant of x times tangent of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. And while the derivative of tangent is secant squared, the derivative of cotangent is negative cosecant squared. So there's some sort of mirror images with the derivative of tangent being secant squared. The derivative of the cofunction, cotangent, is negative cosecant squared. I want you to notice that the derivative of all of the cofunctions, derivatives of all three cofunctions are negative. Derivative of cosine is negative sine, derivative of cosecant is negative cosecant cotangent, and the derivative of cotangent is negative cosecant squared. And then the derivative of secant and cosecant are closely related. derivative of secant is secant times tangent. Derivative of cosecant is negative cosecant cotangent. So you can, and so almost imagine that this is going to come from this, knowing that this derivative is supposed to be negative. If I just add a CO in front of that one and a CO in front of that one, I have this derivative. And the derivative of tangent is secant squared, so the derivative of cotangent is negative cosecant squared. Derivative of sine is cosine, and the derivative of cosine is negative sine. So those are our rules. There are basic rules. We will use these derivative rules just directly without using these limit definitions of the derivative anymore. But hopefully you will remember that the derivative function gives you the slope of the other function. So we can explore that geometrically by looking at the graph of all three of those trig functions, and then inferring what the slope is, and then plotting the slope on a different curve, and then connecting those points to get the derivative functions. Always want to remember that derivatives are actually giving you the slope of the original curve at a particular location x. But let's apply some of these rules now. In practice, you might be asked to compute the derivative with respect to x of 5 times sine of x minus 3 times cosine of x plus 2 tangent of x divided by 3 minus secant of x over 4 plus cosecant of x times 4 divided by 5 plus cotangent of x. And we know that the derivative of a sum is the sum of the derivatives, and the derivative of a constant times a function is the constant times the derivative of that function. So if I want to take the derivative of this sum, I just bring that 5 down. The derivative of 5 times a function is 5 times the derivative of the function, and then I say that's going to be 5 times the derivative of sine of x, and the derivative of sine of x is cosine of x. So we just apply that rule, and then when I'm subtracting a new function, say, okay, well, I'll just subtract the derivative of this. The derivative of a constant times a function is the constant times the derivative of that function. And the derivative of cosine of x that's derived was negative sine of x. Make sure you put that in parentheses to indicate that you're multiplying rather than subtracting that sine of x. Now here, that multiplying the tangent by 2 and then dividing by 3 is the same as multiplying by 2/3. So I would factor out the 2/3. Then I'd say this is going to, the derivative of this is 2/3 times the derivative of tangent of x. We derived the formula to be secant squared x. Here, the implied constant is a negative 1/4. We'll have a negative 1/4 there, and then we multiply by the derivative of secant of x, which we'll derive later using the quotient rule. Turns out to be secant of x times tangent of x. Here, the implied constant, we've got cosecant of x times 4 divided by 5. Is a 4/5 times the derivative of cosecant, which is negative cosecant of x cotangent of x. And then we'll add the derivative of cotangent of x, which is negative cosecant squared x. And then we simplify. Negative times a negative is positive. That's just us applying the rules and then factoring out constants as appropriate. Positive times a negative is a negative. That's easy breezy. We will, again, do the derivation using the quotient rule in another video for these. Then we'll also look at the graphs and explore them geometrically. Actually, let's do that now. So let's look at the derivative of secant of x and then graph secant of x times tangent of x and infer sort of why this should be the slope of this. So this is our secant graph. Now, in order to graph or think about this secant graph and its derivatives, I might look at the tangent lines at each of these bottom points. Now remember, secant of x is just 1 over cosine of x. So let's graph cosine of x as well. We know cosine looks like that. And the secant of x is undefined whenever the cosine equals 0. So we're going to have horizontal tangents, or excuse me, vertical tangents at all the odd multiples of pi over 2, because that's where the cosine is 0. So at negative 3 pi over 2, we get a tangent line. And then negative pi over 2 is going to be similar. Negative 5 pi over 2 is similar. And so forth. We have the positive versions of those as well. All right. So our secant function is undefined at all those values where cosine is equal to 0. And then whenever cosine has a minimum or maximum value of 1 or negative 1, that's when our secant has a horizontal tangent line. So at actually let's add some tick marks on the axis in terms of pi. So at negative 2 pi and negative pi and 0 and pi and 2 pi, our secant function is equal or has a horizontal tangent line. So at each of those points, our graph should have our derivative function should be equal to 0. So I should have a derivative of 0 at negative 3 pi from that value right there. And the same is true at negative 2 pi, negative pi, and then 0. Got all of those function values there. And the same is true at all of the positive multiples of pi. So at pi, at 2 pi, and 3 pi. So our slope is equal to 1 at each of those points. Now, on one of these branches that's going up, let's just focus on maybe this one in the vicinity of the y-axis. Wait, the slopes to the right of 0 are all positive. Let's say we want to draw the tangent line at y equals pi over 2. Excuse me, or x equals pi over 4. Well, that tangent line is going to go right through here, and then it's going to have the same function value as the secant graph, and then we'll have a slope given by secant of x times tangent of x. But let's see. If I want to graph the tangent line at pi over 4, we'll find y or f prime at pi over 4. Actually, I'll just write m tangent equals secant of pi over 4 times tangent of pi over 4, because we know this derivative of secant is secant times tangent. And the tangent line would be given by y equals the secant of that value. So that's the original y value plus the slope of the tangent. times x minus pi over 4. And so if we graph that, we see that that's tangent to the curve. But if we think about how that changes as, let's say, some value a increases, at 0, we have a tangent line with a slope of 0. And then as a increases, this tangent lines get steeper and steeper. So that looks like, let's see, the slope is 0.82 or 0.83. And then as we get closer to pi over 2, the tangent gets almost vertical. Pi over 2 is about 1.5. It's a little bit more than 1.5 because pi is a little bit more than 3, right? So we're going to have a tangent line that's nearly vertical there. But all of those tangent lines are have positive slope between 0 and pi over 2, but they're getting steeper and steeper and steeper. Now, as we go from negative pi over 2 to 0, all those tangent lines have negative slope. We know that because as we look at the tangent line from left to right, it's decreasing. But as we get closer to pi over 2, that negative slope gets larger. So what I would expect on this interval between negative pi over 2 and 2 is a function with negative values over here and positive values over here. So let's graph y equals secant of x times tangent of x. On the interval from negative pi over 2 to pi over 2. And let's get rid of that tangent line now. And so you can see it's what we would expect. Got negative slopes on this side, positive slopes on this side, 0 slope on this side. Now, when we look at the tangent lines on a branch from, say, negative pi over 2 or negative 3 pi over 2 to pi over 2, we're on a branch over here in the vicinity of pi. So maybe we need to come up with a values near pi, negative pi. And let's graph the tangent line now. That tangent line has a slope of 0, so our derivative is equal to 0 there. And then as we decrease a, I'm going to add a slider for a. And we want to be between negative pi over 2, so that's between like about 9 over 2 or between negative 4.5 and negative 1.5. And now we'll just add that slider. And then make sure we draw the tangent lines. We have a defined in more than one place. Okay. So there we add our slider. And notice that those slopes are all positive between negative 3 pi over 2 and 2. And the slope is a very large positive slope, say 7.44 when a equals negative 3.5. But as we get closer to a equals approximately negative pi, which is about negative 3.14, those slopes decrease. They're still positive the whole time, but they're decreasing and they're getting closer to 0. And then at a equals negative 3.14, our slope is nearly 0. It's a little bit less than 0 because this is a little bit less than pi. But then as we go from negative pi to negative pi over 2, those slopes are continuing to decrease, but now the slopes are all negative. The graph is sloping down as we go from left to right. And we're going to plot, we're trying to draw a graph that has these values on it. And we can do that if we just graph y equals secant of x tangent of x. That's what I told you the derivative is. We haven't actually proved it. And that's consistent with our expectation because the slope is positive here, 0 here, and negative here. And then all of the other branches for the secant graph are going to look very similar. So let's look at all these guys. Let's get rid of these. We don't need those vertical lines and we don't need the cosine graph anymore. Our secant of x tangent of x looks like that. And so we're going to have that repeating over and over again. So we can graph that without the secant graph if we want to. And that is the derivative of this graph, which is consistent with our expectation. Positive slope, zero slope, negative slope. Positive slope, or excuse me, negative slope, zero slope, positive slope. So we're going to have negative values, zero value, positive. And then it keeps repeating. And for the blue graph is, or the teal graph, secant graph, and then those white branches. So I think I want to use a different color represent its derivative. All right. So that was just helping us to infer that the secant should look like those branches that we saw, and then to graph that with the secant of x tangent of x, just to convince ourselves that that's true. And again, we're going to prove this using the quotient rule later. We could do something similar with the cosecant graph and the cotangent graph. One thing that's a good exercise that you can do is to just graph the cosecant graph and graph the cotangent graph on graph paper with a grid on it, and then try to graph the derivative graph yourself. So I would recommend that you graph those derivatives by hand and then graph these functions using decimos.com or another graphing calculator and see if your graph matches these graphs. And if your graph disagrees with these graphs, then you can correct your mistakes by looking at this original functions, looking at the slope, thinking about the slope, and see how those slopes should relate to those pictures. And then we can look at what these pictures look like, again, using a graphing calculator.